Alright guys, welcome back to the second part of our video here. This is lesson 1.5. This is part 2 of the video. We're going to look at 2 more of our ideas. We said there's kind of 5 ideas in this section, so we'll try to knock off 2 more of those ideas in this section. Okay, our next idea is the ranges of the trig functions. If you think back to domain and range, range are the values that you get out. Those are your y coordinates, the ranges. So we're going to put in angles into our trig functions. And the question is, what comes out of the trig functions? And at first, maybe you just want to try this a little bit for sine or cosine or tangent. Maybe just use a calculator or something like that. We'll try maybe sine, maybe we'll try tangent just for a minute or two and see what we can get out here. So let's pull up our calculator. Let's put this where you can see it. Make sure your mode is in degrees if you have a graphing calculator. And then let's just try a few of these. Let's try the sine. Let me scoot this up just a touch there. All right, I think we got it all on here for you. So let's try the sine, something like 0. Or let's try the sine, I don't know, something like 30. Let's try the sine of something like 60. We're just trying to go. We're looking at these values that are coming out of here. And oops, get those on your screen there. And the question is going to be, what could they be? We got a 0, we got a half, we got a 0.86. I wonder what's the largest value we can get out of there. That'd be a good question. Oops, let me close that now that I wrote in that. That'd be a good question, though. What's the largest value? So let's try the sine of 90. Look at that. We got it up to 1. We can just focus on this screen there. Pull that calculator back up. Sorry about that. All right. Sine of 90 is 1. Let's try sine of 120. Does it keep getting bigger? It seems to kind of turn a corner and go back down. Try sine of 150. And it keeps going back down. And you can try some other ones as well. All right. Let's try the same thing for tangent. Let's try the tangent of 0. Is 0. Let's try the tangent of 30. 0.57. Tangent of 60. It's getting bigger again. Tangent of 60. Oh, look, the tangent does get bigger than 1. You can try the tangent of 90. It's not going to work, but let's just try it. Tangent of 90, we get undefined. So we get an error, so you can't even take the tangent of 90. So let's try instead, I don't know, the tangent of 89. 57. Let's try tangent of 89.999. A bunch of 9s on there. And look at that. We have, what is that? 572 million. And so it seems like the tangent we can make about as big as we'd like to make it. And let's just do the cosine real quick too. Cosine of 0. Oh, look at that. Already starts with 1. And then we do the cosine of 30. So it's going to shrink down. Cosine of 60. Keep shrinking. You can play with this a lot more angles in your calculator. Try anything. Cosine of 90. Is it going to keep shrinking? Yeah, it goes to 0. What do you think happens then? Just like the sines that turn a corner here and go the other way? And it does. Yeah, it's negative. Goes back to 0.5, etc. Okay, so you can play around with that a little bit and see what you get out. But if you think about it in terms of the definitions, sine was y over r, and r was the hypotenuse of the triangle. So would it make sense to you the hypotenuse is always the biggest side? And maybe you could have a tie, you kind of let the lines overlap. It's not really a triangle anymore. So maybe y, x could be 0 and y could be everything. So what's going to happen because of this definition, sine is y over r, sine is never going to get bigger than 1. It'll be between -1 and 1. It'll never get bigger. Same thing with the cosine. Look, you got your r down here, your hypotenuse. X is on top. It will also be between -1 and 1. And then you get your tangent. And the tangent, guys, you're just picking any y coordinate, any x coordinate. It's unlimited what you pick, so that you can choose any y you want, choose any x you want. So the tangent, it turns out, can be anything. All right, and again, if you think through that, that should make really good sense to you. If not, certainly ask, and we can explain that more in class. But here it is, oops, not there. Here it is, summed up, and these will be facts that you would just want to know off the top of your head. The sine is always between -1 and 1. Same thing with the cosine. Always between -1 and 1. And then the tangent could be anything at all. Okay. Then if we think of our reciprocal functions, since the tangent could be anything, when you go to take the reciprocal, you could make the reciprocal anything you want. All right. Now when it comes to the secant and the cosecant, also reciprocals, think of the sine. If the sine were a half, then the cosecant is going to be 2. Or if the sine were 2/3, the cosecant would be 3/2. But every single time, the sine is going to be a number less than or equal to 1, between -1 and 1. So when you take the reciprocal, look at that. The reciprocal of a number less than 1 turns out to be a number bigger than 1. So it turns out the cosecant is either going to be bigger than 1, bigger than or equal to 1, or in the case of negatives, less than or equal to -1. And likewise for the secant, it'll be greater than or equal to 1, or less than or equal to -1. And these will be facts, again, I put here memorize, better if it makes sense to you. If you just kind of think through that logically, you can again ask that more in class for clarification. But if it makes sense to you, even better than just memorizing it. Okay, where will this come up? Problems like this. You work through a whole problem, you get this answer, ooh, sine of theta equals 2. You say, wait a minute, that's not even possible. So you know somewhere in your problem, you've got a mistake. So is this possible? Nope, that is not. Could the tangent be 0.93? Yep, tangent can be anything. So if you get an answer for a tangent, there's no way if you know what's right or wrong, because anything's possible for a tangent. Could the cosecant of alpha, that's the Greek letter alpha, could the cosecant equal a half? No way. The sine might be a half, but as soon as you take the reciprocal, the cosecant, it's got to be bigger than a half. So that is not possible. And over here, could the tangent of beta be 2? Sure could. Could the cotangent of beta be 3? But the catch is we're using the same letter here. And we know tangent and cotangent are related to each other. They're reciprocals. So if I told you the tangent of beta was 2, you would tell me back the reciprocal, the cotangent, is 1/2. So each of these facts separately are perfectly fine, but join them together with an and that fact is also not possible. All right. Let's get to the next idea. I was kind of looking at the time here. Let's get to this one. All right. Next idea is called the Pythagorean identities. And you remember back in section 4, we had this fact, x squared plus y squared equals r squared. So x squared plus y squared equals r squared. Well, come through this fact and pick either x or y or r. It doesn't really matter. I'm going to start with r and divide both sides by r squared. If you want, you can divide both sides by x squared or by y squared. Divide them all by r squared, and I get x over r squared. I get y over r squared. And over here I get a 1. And you're supposed to look at it and say, wait a minute, x over r, I know what that is. That's the cosine of theta. We put the square there. Y over r, that's the sine of theta. Squared. And I get 1. And you get what are called the Pythagorean identities. That was sine squared plus cosine, or cosine squared plus sine squared, equals 1. Come through, and instead of r squared, divide by x squared, or divide by y squared. Let's go y squared, y squared, y squared. Let's take this over here. X over y, isn't that the cotangent? Squared. Y squared over y squared is 1. And r over y, isn't that the cosecant? So you can kind of see we can drive any of these 3 identities, called the Pythagorean identities. And again, right now in this section, there's getting to be quite a few things to memorize. And later on, you will definitely need to know the Pythagorean identities. They're very, very important. They probably came up in the ACT if you took that recently, or if you're going to take that in October. But for right now, you don't have to memorize it, and then later it will come up again in a later chapter, and at that point, I'll make you memorize it. All right, so how would you use something like this? Well, say they gave you the cosine, and they wanted to know the sine. Well, look at this identity right here. It's got a sine and a cosine in it. So let's try this. Let's go sine squared plus cosine squared. And cosine squared, oh look, cosine right there is a half. So I have 1/2 squared equals 1. So I'm just using this identity and I'm subbing in. Well, 1/2 squared, I know what that is. Oops, that's a little sloppy there. That's a plus. 1/4 equals 1. Subtract 1/4 from both sides. So sine squared equals 3/4. And I know to get rid of a square, I take a square root. So the sine of theta is the square root of 3, because I don't know the square root of 3. The square root of 4 is 2. So square root of 3 over 2. I took a square root, so I put a plus or minus on this. And now the question becomes, what is it? Is it plus or is it minus? And guys, look at this. We're in quadrant 1. Remember A-Smart Trig class? Hope so. Wasn't that long ago. A-Smart Trig class, quadrant 1. They're all positive. So we're going to take the positive value here. The sine of theta is the square root of 3 over 2. So don't go for the negative one. We're in the first quadrant. I'm going to go for the positive one. We're going to do a couple more of these, but I think for this video, if you have the idea, you're in a good spot. You can make it slightly trickier, so do tune into the next video. But this gives you a good feeling for what we've done with this fourth idea.